name is Fufa Beyene from Addis Ababa University. I'm also a member of course Combinatorial Research Studio, and this work is as part of my PhD study supervised by Professor Roberto Mantaci, and as of abstract, we have studied a permutation code introduced by Mantaci and Rakotondrajao. It is well known that the famous inversion code of Lemmer is related to the insertion sorting algorithm. And here in this paper, we show that the MR code, the one which we are referring to, MR code here is the code introduced by Mantaci and Rakotondrajao. This code is related to the selection sorting algorithm. And also we deepened the study of the relation between the MR code of permutations and the statistic between these codes and anti-exceedances of permutations. Further, we relate these MR codes to the cycle structure of permutations. Finally, we present the graphical constructions. As of the outline, I will give this talk on major points listed here, introduction part. And the second section, we will see MR code and exceedances. Also, thirdly, MR code and the cycles, graphical representations, the variant Phi Tilde, conclusion, and finally, the rest acknowledgement. So in the introduction part, I can say here, for over a century, permutations over the set N have been coded with integer n tuples of the form A1, A2 up to AN. For instance, the Lemmer inversion table is related to the sorting algorithm, insertion sorting algorithm. And we define the inversion table of the given sigma permutation as this vector or n tuples of non-negative integers, where i's entry ai is the number of elements j to the left of I, such that j is greater than I. For instance, if you take this sigma permutation in the symmetric group of length 7, 3, 1, 7, 4, 6, 2, 5, you see that the inversion table is 1, 4, 0, 1, 2, 1, 0. Which means for take 1 here, which has only one element largest than it to the left. So we have 1 here, and similarly we can calculate these values. The other code we can also list as an example of permutation code is the Dinnerty code, which is related to the famous combinatorial problem, specifically problem of statistics on set of permutations. When we consider the Lemmer inversion table for any permutation, we see that we have this property that 0 is less than or equal to an minus I plus I less than or equal to I minus 1 for all I. We have also similar property for the MR code. Actually, this MR code is introduced in 2001 by Professor Roberto Mantaci and Phi Tilde. So you see that it satisfies the following condition given by 1 less than or equal to Fi less than or equal to I for all I. And we refer to those MR codes satisfying this condition as sub-exceedant functions. And further, we need some notations and preliminaries. For instance, this is the set of the first n positive integers. Here we have the symmetric group of permutations on this set denoted by capital Sn. And when sigma is taken from this set, we denote it by sigma of 1, sigma of 2, up to sigma of n, or these are images of the integers 1 to 3 in order, in their natural order. So we have this notation. Further, capital Fn is used to denote the set of all sub-exceedant functions over n. And f an element of fn is given in word as f1, f2 up to fn, where fi is just to mean f of I. So take, for example, n3, the set of sub-existent functions on n is equal to 3. We have 6 different sub-existent functions, 1, 1, 1, 1, 1, 2, and the like. So for each sub-existent function, we associate 2 different parameters. The first one is the set im of f, the set of images of f, and the other one is ima, the set of number of elements of set of images. Just the cardinality of the set of im of f is given by ima of f. Further, we need this convention when we multiply 2 permutations, or when we compose 2 permutations, always the leftmost permutation acts first. Let me remind you about the bijection phi introduced by Mantaci.
May I ask those who are not presenting to mute their microphones? Thank you. You can go ahead.
Okay, thank you. This bijection phi is already introduced in the paper of Mantaci and Rakotondrajao. So it is given by the mapping from set of sub-existent functions into the set of symmetric group of permutations defined by sigma, which is equal to phi of f, where phi f sigma, or the permutation corresponding to f, is defined by the product of these transpositions in this order from left to right. And we have example for this. Take f in f9, it is sub-existent function of length 9. It is image here is a set of distinct values here in this.
Stephen has a question. I don't know whether Stephen, will you write the question in the chat room? Thank you.
Okay. So may I proceed, or?
Please go ahead.
Okay, thank you. So we have here image set of 1, 2, 3, 4, 5, 6, and that is size or cardinality 6 here. So to calculate sigma, you just take the product of these transpositions, and these transpositions are taken from the values here, the positions, in order 1, 2, 3, 4, 5, up to 9, 1 with 1, 2, 1, 3, 2, 4, 1, 5, 3, and the like. So when you apply the product of permutations from left to right, you will come up with this permutation in S7. As the MR code, or the mapping phi, is bijective, we have its inverse, which is calculated by n-step procedure. We have sort of algorithm here. So to evaluate the inverse of phi, we first set fi, which is equal to sigma of I. Starting from n minus 1 up to 1, you set first f1i, sigma of I, and then iterate over I to calculate sigma in word. And the second step here is sigma, which is equal to sigma times the transposition I, sigma of I. So this means you simply swap the image of I and I in sigma as a word. This can also be seen in this example, sigma 23154. Then we have the following steps, 5 different steps to come up with f, which is equal to 11144. So we first find sigma of 5 will be f5 is equal to 4, and then swap 5 and 4 to get this one when 5 is fixed, and you take f4, which is equal to 4, and you do similarly swapping 4 and 4 here to come up with 23145, and you take sigma of 3, f3, which is equal to 1, and then swap 1 and 3 to get 21345, F2 then is 1, and the swapping 1 and the 2, you will have 1, 2, 3, 4, 5, or the sorted permutation, and then we have F1, which is equal to 1. Now you read the sub-accident function from bottom to top, and this is simply a selection sorting algorithm. So we have the result that MR record is related to the selection sorting algorithm, and of course the selection is selection of the maximum. There are different methods to calculate sigma from F or F from sigma rather than the product of transpositions. For instance, here we have the insertion method, and Mantaci and Rakotondrajao showed sigma can be obtained from F according to the following insertion method. Suppose that the first I minus 1 integers have already been inserted, then replace the integer f of I by I and append the integer f of I at the end. So take the example here, f is 1, 1, 2, 1, 2, 3, 5, 3. If you assume that already the first 5 integers are inserted, then we have f5, which is equal f6, which is equal to 2. So you look at the integer 2 in this permutation. I hope you can see my cursor here. In this permutation, 3, 4, 5, 1, 2, there is 2 here at the end. Then you replace this by 6 and append 2 at the end. That is how the insertion method works. And read here F7, 3, and look at the integer 3 in this one. It is here. So you replace it by 7 and attach 3 at the end. So finally, you will come up with the permutation 7, 4, 5, 1, 6, 2, 3. Another important thing is some definitions regarding exceedances, anti-exceedances, and weak exceedances. The first one is for the given permutation sigma, we can define the position I in this sigma as exceedance if sigma of I is greater than I. And when you collect all such positions in the set, you will have exceedance set. So the exceedance set of sigma is denoted by this notation, and that is defined by the position I in N for sigma of I is greater than I. For instance, take sigma here, and you see positions 1, 2, and 5 are exceedances. So the exceedance set contains 1, 2, and 5. And also weak exceedance, the position I is said to be weak exceedance if sigma of I is now greater than or equal to I. Exceedance is strict greater here, and we have greater than or equal to for weak exceedance. In this permutation, in the same very permutation here, you have set of weak exceedance, set containing 1, 2, 3, and 5. Because here, in addition to exceedances, 3 is the position of weak exceedance as it is fixed point. So weak exceedance includes exceedances and fixed points. Further, we have anti-exceedance. Again, the position I is defined to be anti-exceedance if sigma of I is less than or equal to I. So the set of all such positions I is defined to be the set of anti-exceedances, and we denote this by this one. Similarly, we have in this permutation, the positions 3, 4, 6, and 7 are anti-exceedances. And Mantaci and Rakotondrajao showed that these are all enumerated by the famous Eulerian numbers. And these are statistics over the set of permutations counted by the famous Eulerian numbers. Finally, as part of introduction, I just talk about the result from the Stanley book, Richard Stanley book. The number of permutations sigma in symmetric group here with k exceedances, as well as the number of permutations sigma with k plus 1 weak exceedances is equal to the Eulerian number ANK plus 1. Mantaci and Rakotondrajao showed that the cardinalities of the set of sub-accident functions f with imma k satisfies the recursive relation of the Eulerian numbers a and k, and I hope you all are familiar with this beautiful and famous Eulerian recurrence relation. A and k is equal to n minus k plus 1 times a n minus 1 comma k minus 1 plus k times a n minus 1 k. Now we proceed to the results we have found in this work, and we have here MR code and the relation with anti-exceedances. Mantaci and Rakotondrajao in their paper noted that the set of images of anti-exceedances coincides with the set of images of the corresponding sub-accident function for f is phi inverse of phi, sigma. So we state this more precisely in the following proposition. If phi of f is sigma, where f and the sigma are given this way, for every anti-exceedance I of sigma, you see that f and the sigma coincide. This implies that f and the sigma differ only in the exceedances of sigma. You can take the following example. F is this one, and the sigma f, when calculated by using either the product of transpositions or the ones that I have mentioned earlier, insertion method, you have this permutation over 10. And consider anti-exceedances are positions at 3, 4, 6, 7, 8, 9, and 10. So sigma of 3 is 2 here, and you observe here f of 3 is also 2. Sigma of 4 is 1, f of 4 is 1. And on all these positions, both sub-accident function f and sigma coincide each other. And we have characterized the positions where these anti-exceedances occur when one only knows the permutation MR code. So the characterization is given as follows. Take f here and that is corresponding sigma here. Suppose that I1 less than I2 up to less than ij is the set of all occurrences of a fixed integer k in f. Then sigma has an anti-exceedance at ij. Ij is the rightmost of these positions. So at that position we have anti-exceedance, and the first j minus 1 of these positions correspond to exceedances of sigma. For instance, if f is this one, you have sigma corresponding to it is this one. So the red one here in f are just the rightmost values. So 5 is the rightmost value, 3 is another rightmost, 4 is the another rightmost. So 1 and the 2 here are the rightmost values. And when you see 1 has 4 occurrences, and in this case you read positions 3, 6, 8, 9, and 10 are positions of anti-exceedances, and the positions 1, 2, 4, 5, and 7 are exceedances of sigma. So simply using f, you can determine exceedances and anti-exceedances of the corresponding sigma under the MR code. Another part of our study, sorry. Question or any suggestion? Okay, let me proceed. We have cycle structure of a permutation. It is well known that permutation can be represented by product of disjoint cycles. As in the following example, you can see this permutation in word is given by the product of these disjoint cycles. 3 cycles, the first one of length 5, the second of length 3, and the third one singleton. This representation more closely reflects the action of permutation, and MR record appears to be related to the cycle structure of permutations. And for that, we have the following basic theorem, the basic result we have found in this paper. So take sigma in permutations, sigma Sn, and the corresponding sub-accident function f. Now, Fi, the i's entry of our f is calculated by the power of sigma to the power of t of I, where actually this t is the minimum positive integer such that sigma raised t of I is less than or equal to I. So this is true for all I, and when I corresponds to the anti-exceedance of sigma, obviously we have t which is equal to 1. For exceedances, we have t actually greater than 1. An immediate consequence of this theorem is if f of I and f of j are equal, then I and j are in the same cycle of sigma. So the above theorem states that Fi is the integer k less than or equal to I, and the closest to I in its cycle when we follow the cycle orientation. This can be explained better in the following example. So take sigma in its cycle representation here. In its word, we have also here. So the blue one here in this graph represents sigma, and the red one represents the corresponding f sub-accident function. So we have 1 to 10, 10 to 7, 7 to 9, 9 to 2, to 6 to 4, 4 to 5, and 5 back to 1. Again, 3 is to 8, and 8 goes to 3 in sigma. So when we apply the above theorem to calculate f, we see that 1 has closest integer in its cycle less than or equal to itself, just itself. So we have f1 is equal to 1, and 10 goes to 7 here. I shall better consider here only the exceedances. For example, 2 is exceedance. So the closest integer in its cycle, in the cycle of 2, less than or equal to 2 is 1. So following the cycle structure, the orientation of this cycle, you see that 1 is the closest integer in its cycle, less than or equal to 2. So f2 is 1 again. And in general, we have f obtained from here 1, 1, 3, 1, 1, 4, 2, 3, 2, 7. Okay. Further, we have the main theorem here also suggests this new interpretation of the integer fi and a new algorithm to go from f to sigma, where sigma is represented in the form of cycles, not as a word. And we have, as a result, the following proposition. Take f in fn, then sigma is calculated as follows. Now sigma will be obtained in its cycle representation form. We start with I, 1, 2, 3, up to n in order, and do the following. 1, if fi is equal to I, then we add a new singleton cycle consisting of I. And if fi is less than I, then insert I before fi in its cycle. So doing this for all I, you will come up with sigma described in its cycle form. In the following example, we see how the above proposition works. And for I from 1 to n, we have these two procedures, as I've mentioned earlier. So take f, for example, this one. Now we start with f1, which is equal to 1. So we form a singleton cycle consisting of only 1. f2 is 1. So we look at the cycle where 1 is and add 2 before 1. And F3 is 3. We don't have 3 in this cycle, so we add a new cycle consisting of only 3. F4 is 2, and 2 is in this cycle, so we add 4 before 2 in the cycle of 2. F5 is 5 here. We don't have 5 in any of these cycles, so we add new cycle consisting of only 5 here. And we proceed the same way to finally come up with the cycle containing 47291 times 863 and 5 here. So when you convert this into Word, you have this permutation corresponding to this sub-exident function. The other one is the graphical representation. We again apply the main theorem described earlier to do with the graphical construction. And we have these two definitions. The graph of sigma is given by set of points having coordinates I, sigma of I represented on the x-axis, and sigma of I on, or the value of sigma at I on the y-axis. Similarly, the graph of f will be represented by a set of points having coordinates I, fi. So we have the following proposition that describes how to evaluate f from sigma. So take sigma in Sn. Its corresponding sub-exident function will be evaluated according to the following procedure. For all I, we begin with the largest value n and go down to 1. If the leftmost point of the line y, which is equal to I, is higher than the diagonal y, which is equal to x, then reduce its y coordinate by moving it down on the same level as the point on the line x, which is equal to I. So this is the procedure we follow to use the graph of sigma in order to evaluate f. So this will better be explained in the following example. Take sigma here in S9. You can use whatever method you want to come up with the corresponding sub-exident function. F was equal to this one. Now we see how to apply the above procedure, graphical construction, to come up with the graph of f from the graph of sigma. So the first graph here is the graph of sigma, and the second one is the application of the proposition or the procedure, and the third one is the graph of the corresponding sub-exident function f. Now we have the graph of sigma here, and the procedure says begin with I, the largest value n, go down to 1. If the leftmost point of the line y, which is equal to I, is higher than the diagonal y, which is equal to x, then we move down this y coordinate into the same level as the point on the line x, which is equal to I. So from this, we have at 9, sigma of 9 is 9, exactly on the diagonal. So for I, which is equal to 9, nothing happens, and our point stays or remains there. For I, which is equal to 8, we have this point, which is above the diagonal. So now we move this point to the level x, which is equal to 8. So we have at x, which is equal to 8, you have point here as a level I, which is equal x, which is equal to 7. So you move this point down to this level, and similarly go to the left. For I, which is equal to 6, we have point here, which is already below the diagonal, nothing happens. And take I, which is equal to 5 here, we have the point above the diagonal. Right here, our y, which is equal to
Fufa.
Okay.
For I equal to 5, you should look at the point with y coordinate equal to 5. So for when I equal to 5, you are acting on the point 1, 5.
Yeah. Yeah. So for I5, we have, no, for I6, I'm talking about I which is equal to 6 here. So this point will be moved down to x6 here. So we have the point here. You move this down to this level. And when you consider I which is equal to 5, you have this point, and that is above the main diagonal. So look at x which is equal to 5, and at 5, you have the point at the level 2 here, and this point will be moved down to this level. And you go next to 4. For I which is equal to 4, the corresponding point is here, 2, 4, and it is above the main diagonal. You look at x is equal to 4 here, and at x is equal to 4, you have point at the level y is equal to 3 here. So you move down to the level of this one. So
Fufa, you have about 10 minutes left, so you should do.
Okay,
a plan
thank you.
Within
So
10 minutes.
following the same procedure, you will have this resulting graph, and this graph is associated to the sub-accident function f, this one. So this is how we can use the graphical construction to construct f from sigma. Conversely, we consider the graph of f, and we again follow the following procedure to construct the graph of sigma. For all I, now in increasing order from 1 to n, move the leftmost point of the line y which is equal to fi, different than I comma fi up to the level y which is equal to I. And we have the following example for this. Take this graph of f, and we now start from I which is equal to 1 and proceed to the largest value 9. So for I1, you have nothing happens, our point remains there. And for y which is equal to f2, f2 is 1 here, and the leftmost point is 1, this point at 1, 1. So you move this one into the level 2 here, because you move this one into the level y which is equal to I. And for y which is equal to f3, you have f3 is equal to 2, y which is equal to f2 on this one. The leftmost point is here, the point 1, 2, and this point will be moved to the level 3 here, because the x coordinate here is 3. So we follow this procedure to come up with this resulting graph, and this graph is the graph of permutation sigma given by this one. So we have this to reverse the action of our construction given in the above proposition. Finally, I will say a few words regarding the variant Phi Tilde. This Phi Tilde is also MR code, but when we define, it is given by the product of transposition here in the reverse order. Earlier for phi, we have taken the product from 1f of 1 to f of 2 up to this one, but now we consider the product in the reverse order. We have the product of this transposition from left to right. If you have f here, applying phi tilde here, you will see that sigma is this one. Now you take your product of transpositions in decreasing order. And it is very important to note here that phi of f is equal to sigma if and only if phi tilde of f is sigma inverse. So sigma obtained from phi and sigma obtained from phi tilde are inverse of each other. And in some cases, it is very clear to use phi tilde than the original phi. And analogous results for this phi tilde variant are given as follows. We have insertion method to construct sigma from F using Phi Tilde. The set of images of F coincides with the set of weak exceedances of sigma. You remember that the set of images of F coincides with the image of anti-exceedances in phi, but now we have weak exceedances instead. The rightmost position where certain value k occurs in F corresponds to the value of the weak exceedances of weak exceedance of sigma at position k. The analogous theorem of the main theorem for Phi Tilde is given as follows. We have F obtained from Phi Tilde inverse. I'm sorry for this. Phi Tilde inverse of sigma is F, where Fi is sigma minus T of I. Now you look at sigma minus T of I, where T is the smallest positive integer such that this condition holds. Regarding the graphical construction for Phi Tilde, interestingly, we do not have a procedure to compute the graph of sub-extent function F corresponding to the given sigma via Phi Tilde. That does not explicitly or implicitly passes through the inverse of the permutation. So I have this much, and finally I conclude. In this paper, we have extended the representation of permutation code called sub-exceedant functions, and some interesting results were presented. Different combinatorial interpretations of MR code were given for both Phi and Phi Tilde, and we have further interesting results and some open problems regarding the study of classes of permutations associated with particular sub-exceedant functions satisfying certain particular properties, like non-decreasing sub-exceedant functions for all I that satisfy an integer interval and the like. And some of this can be a part of future presentation. And there are some references here. And finally, I want to acknowledge different bodies. And the first one, I want to express my deepest gratitude to my supervisor, Professor Roberto Mantaci, for his so valuable suggestions and comments throughout my work. In addition to this, I want to thank his institution, IRIF, University de Paris Diderot, for hosting my research visit in Paris for 2 weeks, during which this work was developed. I would also like to thank Professor Paul Vaderlind for everything he has been doing in my work. Lastly, but not least, I would like to thank my university, Addis Ababa University, Department of Mathematics and its staff, like Dr. Tlaun, Dr. Samuel, and there are many staffs here. I want to express my gratitude, and I also thank ISCP for funding my study. And thank you very much. This is all about my presentation. If there is any question or any comments, you all are welcome. Thank you again.
Thank you very much, Mr. Fufa Beyene, for that wonderful talk. I'm happy that despite the fact that you started a bit late, you've been able to finish in time.
Okay.
So if there are any questions to Mr. Beyene, please, this is the time to ask.
Well, I've got a naive question to ask. So what is the, maybe I missed the very first part of the talk, but what is the motivation for studying these MRL codes? Why are they interesting?
Okay, thank you for your question. For almost more than a century, we know that permutations are represented by different codes, and the very famous code is Lemmer code, the inversion table of permutation, and we can also mention Dinert code. And these codes are used to easily represent permutations, and you can better deal with the properties of permutations and some specified classes of permutations when you consider their representations rather than considering the permutations themselves. So in order to read very important properties of permutations, it is very important and necessary to consider their representations in like inversion table or binary code or the one that we have stated here in this paper, MR code. So by using the MR code, you can deduce about a lot of statistics like those I have mentioned in the paper, anti-exceedances, exceedances, weak exceedances, and the like. So that is a very basic reason we are interested and motivated to study these MR codes.
May I add something?
Of course.
You're welcome.
Yeah, there is also another important aspect is when it comes to algorithms that you need to generate, for instance, all the permutations of a certain size. Sometimes it's easier to find algorithm to generate the codes, more efficient algorithm to generate the codes, algorithms that are faster, but they generate the codes and not the permutation, because on the codes, you can easily construct sometimes a sort of successor function that it tells you very easily from one function how to construct the next, so that you construct them all. And you cannot always do that on the permutations. So this gives you usually algorithms, generation algorithm that takes like a constant time to generate every code, whereas that may not be possible with the permutation themselves.
Yeah. Thank you very much.
Any other questions? Mr. Fufa?
I think Olivia is about to ask. Okay, Olivia.
Hello. Yes.
Okay.
Thank you, Fufa, for the wonderful presentation. Now, when you are beginning your talk, you talked about the selection sorting algorithm. And maybe you can just help me summarize or tell me in brief how you use this in your work. Like how, in brief, I just want to know where you use them briefly.
Okay, there is already the algorithm for this, I think, in the introduction part of the talk. In the insertion method, yeah, here in this one, you have in finding the inverse of the map phi here, phi is originally defined from F to sigma. And when you go back to F from sigma, you go through this algorithm. And in this algorithm, starting with any permutation, when you find the corresponding sub-exceedant function, you have the sorted permutation. So you have an identity permutation at the end of your procedure. And this is actually the one that we are referring to, the selection sorting algorithm, because it is every time you select the maximum and the swap with the one at the end to get the next step. And for instance, here 5 is the largest, you swap with 4 to get this one. And doing this repeatedly, you have the sorted permutation at the end. And this is the selection sorting algorithm. And the procedure is given here. First set Fi sigma of I, and then you iterate on I starting from the largest to the value 1 here.
Okay. So use it find the inverse. Okay, thank you.
Welcome.
Yes, we have 3 minutes left for questions.
Okay.
Any questions? Any more questions? There are no more questions.
Okay.
Yes, join me to thank Mr. Fufa Beyene once again for his wonderful talk.